Hi, welcome everyone to our fourth Malware Forum. It will be held in collaboration with Norwegian Cybersecurity Center. So basically, this is the digital forum that we organize this week in Gjøvik. Next week, it will be a bigger conference in Oslo. My name is Andrei Shalaginov. I'm a postdoctoral researcher in digital forensics. And this whole forum basically started by Gyrolov Dirkolbotten, who is associate professor in cyber tactics and malware reverse engineering here at the department. So the whole thing started in 2017, and it's been running for quite some time already. Right, so we are part of the Center for Cyber Information Security, which is one of the largest public-private partnership in Norway in the domain of cybersecurity. So we have a multiple research group working on different topics like critical infrastructure. We have information security and privacy, cyber defense, e-health, biometric, forensics, and so on. We also have multiple partners from all around Norway. So it's not just, let's say, the public organization. We have the police, criminal police, economic police. We have companies like KPMG, Mnemonic, and so on. So there are multiple, it's a big consortium where we collaborate, where we work together on different projects and promote research. NTNU is one of the largest universities in Norway, and it's located in 3 cities. It's Trondheim, Gjøvik, Ålesund. We are part of the Faculty of Information Technology and Electrical Engineering, and we are located in Gjøvik. However, our department, Department of Information Security and Communication Technology, basically located across 2 campuses, Trondheim and Gjøvik. So it's about 100 people working in different areas of cybersecurity and information technology. So the department is focusing heavily on the information security and communication technology. We have multiple national, international projects. We have collaboration. We organize lots of activities in cybersecurity. Here in Gjøvik, we have a heavy focus on cybersecurity. I would like also to mention 3 entities that we are part of. Is Cyber Defense Research Group, with the focus on cyber operations and strengthening the defense in Norway through education and through training and basically knowledge production. We also have NTNU Malware Lab. So Gyrolov is the head of Cyber Defense Research Group and Malware Lab. And Malware Lab basically was founded in 2016 as a then collaboration between digital forensics and cyber defense research group. So the focus of Malware Lab is to increase the, let's say, and foster collaboration between the public and private organization, security organization working on malware analysis, and to develop corresponding body of knowledge to promote the courses. And this malware forum is one of the activities. We have research, so there are postdocs, PhDs, master students, bachelor students working on different topics in malware analysis, machine learning, digital forensics. We have also courses in education part, it's reverse engineering, cyber tactics, cyber intelligence. We have the digital forensics, data science for forensics and security, and so on. We have dissemination, so Malware Forum is one of those dissemination activities that we have, along with cyber defense exercise, Norwegian cybersecurity challenge, and so on. And then we have also national, international training activities like Wikisprang, Norwegian Cyber Range, Digi 2020, and so on. The research of Malware Lab is it's multiple topics that we're exploring, mostly related to automated analysis of malware and classification, like, for example, application of machine learning, graph analysis to detect malware using static dynamic features, using, for example, multiple classes like multinomial classification. And it's also something that we try to develop as a whole, looking into malware types from different platforms like Windows, we have Linux, we have OS X, we have IoT, we have Android. So multiple things that we have in place. So the Malware Forum started 2017 as a part of NSM North-Cert Security Forum in Oslo. It was quite successful for full room in 2017 with 60 participants, and then we kept up with the number of participants in the following year. So this year it's a digital forum, so hopefully next year we can meet again to discuss, and it's organized together with Norwegian Cybersecurity Center. It's part of bigger conference next week. The program for today, we have the introduction. We have two really nice and interesting presentations from Moritz Rabe from FireEye, and we have also malware. So this is the malware ABC from Moritz Rabe, FireEye, and then we have also talk from Kevin Alejandro Raundi from Norton LifeLock. He will be speaking about creepware. This is the program for today. We also have live discussions after the talk. The format that we decided to use is pre-recorded videos from the speakers because we cannot guarantee that the internet connection will be stable. So just to avoid any interruption, we ask them to provide video, but they will be available for Q&A after that. All right, please enjoy the talks. I hope you will be interested in the topics that we will be discussing today, and feel free to join our Q&A session right after that.
Hey, hello, and welcome. Thank you for joining this Malware ABC talk, where I'm going to take a malware sample as a case study and walk through some of the interesting features of this sample, and also talk about some analysis techniques that I like to use, and hopefully you can also incorporate into your future workflows. All right, before we get started, a little bit background about myself. My name is Moritz Rabe. I'm a principal reverse engineer on the Mandiant Flare team. I've been with FireEye Mandiant since 2015. Before I started working with the Flare team, I was a grad student at Carnegie Mellon University, where I obtained my Master's of Science in Information Security. I then lived in the US, Carnegie Mellon University is in Pittsburgh. I lived there for about 2 years, then moved to New York, started working with the Flare team. And then in late 2016, I moved back to Germany, where I'm originally from Wolfsburg, and am based out of today again. On the Flare team, I do malware analysis. So I analyze hundreds of malware samples every year. And with that, I also like to do automations of malware analysis processes. Specifically, some tools that I shared with the community are Floss and Kappa. Floss is a tool that tries to automatically deobfuscate strings from malware. They normally try to hide that from us, and Floss is a tool that tries to make this accessible to even non-reverse engineers to be able to pull out that obfuscated strings. And Kappa is a tool that I'm very excited about. We just released it in the July of this year at the SANS DFIR Summit. And it's a very cool tool, I think. Tries to give you a description of the capabilities of a program. You can use that, of course, to drive your malware analysis, of course. So if you haven't checked those out, please do so. You can find them easily on the FireEye GitHub repository. And if you have any questions, please reach out to me directly, either via Twitter, as shown here below, or via email. That goes the same if you have any questions, of course, for this presentation. What I also like to do is share knowledge and expertise, not just these tools, but also teach classes. So we at FireEye Mandiant, we teach a lot of malware analysis classes, and used to travel all around the world to do so. These days, it's mostly residing to virtual classes, but it's still fun nonetheless. Also, thanks for having me here. Of course, it's a great opportunity to keep the exchange going even in these crazy times. So thanks for having me. Of course, thanks for Michael Sikorski for presenting me with this opportunity. And now let's hop in. So this is going to be a case study focused on this malware family that's known as, under the names Divergent, Nodesoc, or Norther. It's a well-written backdoor, and Has some standard backdoor functionality, supports different commands. It's modular in nature, so it can pull out additional command modules, load them and execute, which is pretty cool. And it can update itself, but that's fairly standard for a backdoor. For its messaging, it uses this kind of interesting functionality where it has JSON messages that are then RC4 encrypted using a hard-coded key that's embedded in the binary, and then that data is base64 encoded. And that's what the malware mostly uses to communicate back and forth with its C2 server. But it's not going to be the focus of this presentation. In here, we're going to focus on the ABC of this malware. And that's going to be the anti-analysis techniques, or the interesting functionalities in this sample, namely the loading process of this malware and the anti-debugging or anti-detection techniques that it features. Then we're also going to look at the bits service that this malware abuses for some unique functionality. Using bits, quite common in malware, but this malware uses it in a unique way, and we're going to look into that. And then we're going to also talk about COM, and COM is a powerful functionality provided by Microsoft. Gives you access to a lot of things. In this malware, it's, for instance, used to perform a UAC bypass. And we're going to look into that and also learn a little bit about COM reverse engineering, and maybe I can share some tricks on how to do it more efficiently. And with that, let's start with the first letter of this ABC here, the anti-analysis. And we're going to start looking at the loading process. This malware starts out to be loaded as an HTA application. You can see at the bottom here, the HTA header. That's a Microsoft HTML application. Basically just contains HTML code, can also contain script code, JavaScript, and or in other cases, VB script. And it's a fairly common technique. There's also a MITRE ATT&CK technique associated with this, where this HTA application is being used to be loaded via the MS-HTA application, which is handy for the attacker as a signed binary. And as opposed to having an HTML document loaded in the browser, this functionality here doesn't confine to any security model. So HTA applications perform in the context of a signed binary and have much more power than just an HTML application in a browser. So for example, they can start processes, read the registry, write files, inject code, and so forth. So this is just one huge line that starts out as the malware first stage, and comes in handy for us to have some deobfuscation tools available. In this instance, it's going to be very helpful to deobfuscate that embedded code. There's some HTML, but for the most part, it's JavaScript. And for that, I like to use JS Beautify, which you can get via Python, you can get in Node.js, or in different text editors. There's different plugins you can embed that. For that, for example, I like to use Visual Studio Code. Everything is embedded quite nicely, and you can use it just after a quick install. Another cool tool you can use is DE4JS, which allows you to deobfuscate JavaScript code as well. So here we just put that script into Visual Studio Code, enable syntax highlighting for HTML, and we can see again that HTA header and then the HTML start. And then quickly we see a script tag. Again, this is not like the nicest way to read it, but we're going to clean this up a little bit further here. But already in the script tag, I can see a reference to the registry key. I can see various obfuscated values. And for us, it's going to be helpful to understand how that comes together at the end. When I say here, the slides here say deobfuscated, but it's not really deobfuscated. It's just beautified. This is an excerpt of the JavaScript code. I can't really make sense out of that. And I wouldn't want to necessarily analyze that just in a static fashion. So for that, I like to use the Chrome developer tools. So here's an example of that. And that's exactly the same code snippet I've pulled up here. In the Chrome developer tools, at least you can put in code, copy it in there. Or what I did here is I created a new HTML document, loaded it up in the browser, set a breakpoint at the top, and then started debugging. And you can inspect different variables here. At the right, you can see that this one variable refers to a reg read and the specific registry value. And then there's some other functionality that happens. When you translate this code, actually, you can see at the bottom here, this is what happens. So it uses the W script shell to do this registry read on that cryptly looking registry value. And then at the bottom, you can also see that eval call that uses the JavaScript eval functionality to execute JavaScript from the loaded registry value. So we can go to the registry, take note of that HXX value at the bottom. And we can see various entries in this registry value here. And the HXX value, again, looks like script. I can also see at the bottom of it that looks like PowerShell script. And there's various binary values, including the value that starts with 4D5A here, which is the typical MZ header. So that's already a good indicator that some binary will be loaded here, and that's likely gonna be it. But let's follow this loading process and see how this all comes together. So we have this eval of the JavaScript. This is the value I'll pull out. This time it's a little bit more readable, so you can inspect the value and you can see pretty quickly that this will likely just start PowerShell and provides some command line arguments. I cleaned it up a little bit, again, using JS Beautify to deobfuscate it and also to beautify the code. And for debugging, of course, you can use the Chrome developer tools again to pull everything together. And this is what it comes down to. It does that shell object and performs a run of that PowerShell. So that executes that PowerShell process, providing that enc argument and a base64 encoded blob. That enc argument for the PowerShell is a pretty interesting functionality provided by Microsoft. They say it's enabled to allow you to execute complicated commands that include apostrophes or curly braces, or really it's to execute malware, because in most instances when you encounter this, this will be used to load some kind of malware. If you Google, you'll quickly find various forum entries where people talk about how they use this enc mechanism to run their type of malware or execute some malicious code. So that's what happens. Let's look at this base64 decoded blob now. So we can just pull that out, base64 decoded, and inspect it. So it's again PowerShell, and this time again obfuscated. So we can use another tool now that's called PS decode, which is quite helpful. Sometimes you have to add additional analysis steps, but it cleans it up for you a little bit. And another tool you can use in conjunction with it, or I use in this instance here, is the CyberChef Beautify functionality that works on various scripting languages and payloads potentially. So that's also worth checking out. Cool tool. And for debugging PowerShell, you can use the PowerShell Integrated Scripting Environment, ISE, that comes with your regular PowerShell installation. So when we clean this up a little bit, this looks like a more readable PowerShell now. Here we see the creation of a registry path. And then in line 8, there's this expression. The comment above that line in line 7, I added, that shows the full path. So again, that's under the software value that we were looking at earlier, and loads another value from there. You can see that line, and then it executes it using the IEX, or the invoke expression, which you can kind of think like an eval in JavaScript. It executes additional commands. And here, that expression, of course, we can check out. We can pull that from the registry and take a look into it. Again, a little bit obfuscated, but you can still read it. What basically happens here is that there's another base64 encoded string that the malware base64 decodes. Then it deflates that stream. So it decompresses the stream, and then again calls the invoke expression on that data. Because PowerShell is a little bit harder to debug, you can just set a breakpoint on the last, after that last pipe symbol. Cool trick you can do is to just change the script, and instead of executing it, writing out data to a file. And that's what I did here. So instead of calling the execute or the invoke expression commandlet, we're gonna save this data out to a file stream on the desktop, and here named it loader.ps1, and we're saving the file data into that file. And now we can inspect the data that was written. And here we notice, again, it's obfuscated PowerShell. This doesn't look as nice, but PSD code helps quite a bit. And in the last line of this whole large script, this is very long, because in total, like almost 2,600 lines. But in the last line, really, you come quickly to notice that this is related to the PowerShell Empire framework, which is an offensive red teamers open source project, which allows you to do a lot of offensive tasks in PowerShell. And here it uses the invoke a memory load library functionality to reflectively load a PE file. And again, that PE file here is read from the registry and then loaded reflectively into the current process, which will be the PowerShell process. So this malware eventually will run within the context of PowerShell or exe. And here is again the registry value starting with that MZ header. So to summarize, this is the whole loading process. We start with the HTA application that's executed by this mshta file. Then we have obfuscated JavaScript, we have obfuscated PowerShell, an obfuscated PowerShell Empire payload, and eventually the malware is loaded reflectively into memory. And all of these steps more or less refer back to the registry, which is quite an interesting way to do this, very convoluted, but it can help with anti-detection, and it definitely can confuse analysis tools and make our analysis as human reverse engineers a little bit more cumbersome. Because one gotcha here in this case is when you just pull out that binary, which is pretty obvious. I would probably just do that from the beginning and pull that binary out. And when you just do that and try to run the malware, it just crashes and brings up this crash report indicator asking if Microsoft can help me to provide a solution. I checked with Microsoft Online. They weren't able to help me with this. But I quickly after looked into the code and noticed that they're actually doing a memset operation on the embedded configuration in the file. And if you load that binary via the standard Windows loader, which respects the memory section permissions, it actually loads that session up as read-only, but the malware does a memset on it, tries to write and modify that internal value, and that crashes. But since this malware expects to be loaded by a PowerShell Empire loader, which just loads this into memory with read-write-execute permissions, it actually works in that case where it's loaded. And this is, I think, another interesting anti-analysis technique. When you just pull out that binary and try to run it in a sandbox, it just crashes after some operations. It gives you some output, but you won't get most of the run trace in that case. So that was quite interesting to see. Now with that, let's hop into the next anti-analysis techniques, namely the anti-debugging and anti-detection tricks that this malware embodies. And it's got fairly standard anti-debugging techniques. For example, this is debugger present check, but then some unique functionality that I haven't seen in any other malware sample before is that it passes this p equals d string, and there's different variants to this post function, and then that function sleeps indefinitely. And what this post message first does, though, is it communicates out to the C2 server and sends the string indicating what debugging check failed. And essentially, it's the first message that the malware sends out to its C2 server, but also the last one in this case, because then it goes into this infinite sleep loop. But it's very interesting to see that kind of this beacon message is the detection of a debugger in a program. So quite interesting to see. Besides that isDebugger present call, we also have a check to check the tick count. That looks like this. At the top, we have the disassembled code. At the bottom is a little bit more readable, the decompiled code. And that simply gets the tick count then performs a sleep operation of 5 seconds, then gets a second tick count value, subtracts the first value that it obtained, and then compares if those values are under 4 seconds. And that is a good detection to notice if the sleep operation was short-circuited or like knocked out, which is a good indicator to be running in an analysis environment, either human analysis or also likely in a sandbox. Another check that's in this malware is this the check of the number of processors, and the malware checks the process environment block for that value. You can see at the bottom here again is the decompiled version, and it checks if the number of processors, according to the process environment block, is less than 2, so it expects at least 2 processors. And this could be a check either if you're running on a very old system, or more likely if you're running in an analysis environment where there's only one CPU set up for that virtual machine. The fourth anti-debugging check that this malware embodies is that it enumerates all processes and gets their executable names, and has an embedded list of CSC32 entries, which it then compares to. And if it finds any of the values present, it just goes again into this post and sleep indefinitely loop. And this is the list. It makes it harder for us to analyze because we can't just read process names, and we want to know like what is this malware looking out for, what doesn't it want to have running, or potentially what of my analysis tools will make this analysis fail. And it made me kind of feel like I'm in a Family Feud game show where I have to guess like what does this process name translate to. The first instance here is Ollie debug, but then we have internally lists of process names that malware normally checks and tries to avoid. And I was able to pull that down, generate the CSC32 values, and then translate or compare them to the values embedded in the malware. And this is the list that I came up with. This is not a complete list, but some interesting functionalities. Looking for debuggers, Ollie debug, windbag, looking for sysinternal suite tools, TCP view, autoruns, filemon, procmon, then also IDA, and tools like Wireshark, and some sandbox related tools like the Joe Box server, for example, from the Joe sandbox tool. A similar thing the malware did for modules that are being loaded into the process. So that's essentially the DLLs that are loaded into the malware. And the malware would enumerate them, again, compare them to a CSC32 hard-coded value list. And what I would check for here is these 5 values. The first one is related to Avast antivirus. The second one is the DLL that Sandboxy would inject into the analysis process. And then those other 3 values are related to the Sunbelt sandbox. So the malware tries to identify those values, and if it detects any, it wouldn't execute properly. To overcome this anti-analysis technique, of course, we can see here there's always these calls, and then it checks the return value of these functions, and then there's a conditional jump. To overcome this, we could just invert the respective conditional jumps here to, for example, make the jump 0 a jump not 0, or hard code it into an unconditional jump to just jump always to the next basic block that we want to see executed. Or what I did is I went into the post function and just knocked out that sleep, either by just overriding all of the call to sleep with knobs, or by setting the infinite value, which is -1 to 0, and then the malware would do the post, but then it would also continue running and go back to the next functionality. Another cool anti-detection or anti-analysis technique that I saw in this malware was that it would get the process environment block again, as malware was quite a lot referring to it. And in the process environment block, there's entries where it indicates the image path name of the current process that's executing and the command line. And the malware would try to overwrite that with benign looking values, for example, of explorer.exe. So the malware wouldn't then show up as a malicious process or a malware process within the task manager or other analysis tools. All right, that's it for the anti-analysis. Now let's switch over to the B of the ABC here, standing for BITS, the Background Intelligence Transfer Service, which this malware abuses in quite an interesting and unique way. So for some context here, the BITS service is provided by Microsoft and allows you to download and upload files in the background. It's aware of potentially a throttle connection. It can be set up to save bandwidth so that the foreground processes have priority. And it's asynchronous in nature, allows you to handle network interruptions. So if you shut down your system and the system was still performing an upload or a download, it can resume that at the same place, even after reboot and after other network resets. It's well documented. It's on MSDN. You can get access to it from a C program, for example, via COM. So that's also a good combination with that third technique or big block that we're going to talk about, COM, in the next section here. But it's normally used to download and upload files. And we've seen that used in malware to enable its C2 communication or enable exfiltration of data. But this malware uses it quite a different way. And what it does is that it uses bits for its persistence mechanism. So you can see I pulled out the information of the setup bits job here. You can see that job file, which essentially just copies notepad.exe to your app, to this app data path. And that happens every 9 minutes. Normally in that you would set like the remote server and would set the local file, but here it just copies that local file to a local file path. And where it achieves the persistence really is in this notification command, because that command will be executed whenever the bits either errors or the transfer completes. And what that then essentially does, it executes command.exe 2 times. And one of these has the command of that HTA application, which was the initial stage of the loading process of this malware. So that is triggered every 9 minutes. The way they choose to implement this also flickers up this HTA application when it starts. It shows up on your screen really quickly, which is kind of funny. But every 9 minutes you'll get that. So it's not the most stealthy way to persist on a system if you have a user using that system. And there's different tools you can use to inspect the bits jobs that are set up on a system. For example, I'm using bits admin in the screenshot here. And the important information is shown in the box that I highlighted, including the job files, which are being copied. And in this instance here for the persistence, that notification command line. Microsoft says this tool is deprecated and you shouldn't use it anymore. But probably when Microsoft says that, it's going to be available for the next 10 to 15 years. But in the meantime, they also provide PowerShell commandlets, which supposedly let you do similar things. But when I ran this get bits transfer commandlet here in verbose mode, it only showed me this information. So bits admin, as of now, most powerful tool to pull out that information. As a persistence backup mechanism, so if that bits mode fails, you can see here, I named that function bits create job. If that fails, the malware resorts to using the good old registry run key, which executes every time the system boots up. And here it just sets up a value and executes that same MS-HTA application to start the HTA file that it dropped on disk. And with that, let's look into the last section, the C, namely the COM usage of this malware. A little bit background, COM is the component object model. It's a Microsoft way to provide object functionality independent of the programming language. COM itself is not a programming language, but it allows to have access to very powerful features on the system. Some examples how you can get to the COM is in VB script using the create object functionality. In JavaScript, the new ActiveX object functionality, you can get to it in PowerShell. And in C or most C++ applications you'll see it being accessed via the co-create instance call. Some noteworthy COM interfaces which provide functionality often used by malware is the Internet Explorer application, which allows you to download files and browse to websites potentially. Then the firewall manager, which allows you to set exceptions in the host firewall. So you can communicate to servers even if the local policy would normally deny that. Then there's access to WMI, so you can query or set values. The iShell link interface allows you to create shortcuts. And then also heavily used in malware is the iTask service interface, which allows you to schedule tasks and persist on a system. When reverse engineering COM, it can be hit or miss. Sometimes IDA is very helpful, sometimes not, and you have to look elsewhere. But what you basically have to do in a binary, if you see that co-create instance call, you have to identify these interfaces. The first one is the interface ID, and then the second one, that class ID. And those are normally references to some bytes in the program. Sometimes IDA, if you apply the right structure and set the right value, it can rename them automatically for you. So here I applied that class ID structure type, and IDA was smart enough to recognize that this is the iBackground copy manager interface. Other times you have to go into the registry and kind of look up the values there. Here's an example. So those reside under the software classes interfaces entry. And here we can see that value 5C, E3, and so forth. And under there, there's an entry which gives us the name. And here, in this case, again, it's iBackground copy manager. I also have a script that helps me analyze that or do that automatically, which I'm going to show the effects on here later. Then reverse engineering COM comes down to browsing MSDN a lot. At least in my experience, I have like many tabs open. Just as a quick example of some stuff I had to when I double checked some stuff for this presentation. A lot of looking up and seeing how these objects relate to each other and what functionality they provide and how they work. But IDA can be helpful here, and in most instances it is. You can load the structures into it, and that has definitions of the vtables that are being used by COM objects. And that makes me very happy when that's available, and I can just input that and apply the structures. So here on the left, we have the plain starting output that we get. There's a call to this virtual function offset, here plus 14 in hex. But I've applied the structure correctly from IDA Pro that I imported. It tells me that this is the enum jobs functionality. And it also then associates the respective arguments for those function calls. So that's very helpful. And here is the effects of a little automated script I normally like to run when I see a co-create instance call, which identifies those calls, then tries to look out for the referenced IDs, tries to identify them. I have a local database. You can pull out the registry, pull out the names, and create an offline database of that. And I did that here. And then you can also try to automatically apply those structure offsets that you identified here. And that helps a lot actually in identifying COM and reverse engineering it, because it's very powerful but can be annoying to reverse engineer. And here's how this malware then uses this COM mechanism to set up this bits job for persistence. First, it enumerates and checks if persistence already is given to the malware by enumerating all jobs, setting or getting the display name of those values, comparing it to the hard-coded value that the malware sets up. And if that value is not present there yet, the malware creates a new job, and in that it sets up that file copy mechanism from the notepad to the app data path, and also that notify command line, which achieves the persistence in the end. Again, there's a bunch of loops you have to jump through here, and it can be very helpful if you have those type definitions in either available. If they're not there by the tool itself, you can set them up from header data or from data from MSDN. Another use of COM in this malware is a UAC bypass. There's a way for COM to perform elevated operations, and in the registry there's a list of exclusions where it doesn't prompt you to use the UAC. And the malware uses that functionality to not show a user account control prompt to the user, and then it can perform some of the functionality it does, which it wouldn't be able to do with just regular user privileges. And the way it does that, it uses this elevation administrator moniker and gets access here in this instance for not via co-create instance, but via the co-get object, and then pulls up the information, sets that moniker, and at the bottom you can see it calls shall execute from that obtained value here, and that essentially elevates the privileges of the program where it starts itself. And a third thing that this malware uses COM for is to disable Windows Defender, at least in part. It gets the antivirus products from the via WMI query that it does via COM. And if it identifies Windows Defender in those entries, it sets registry values that it has hard-coded to disable the spyware functionality, disable real-time monitoring, and some other values that I haven't shown here. And in addition, it also tries to disable the Windows Update in those instances, which is also quite interesting. That concludes the malware ABC here. In conclusion, this is an interesting sample, a well-written backdoor with some interesting and novel functionality. The anti-analysis we saw, it's a convoluted loading process going from HTA to JavaScript to PowerShell, and then through the eventual payload. Not too unusual, but I haven't seen too many public resources of that, so I thought it's cool sharing. Also interesting was to see this beacon message, which sends out that anti-debugging notification basically to the server as its beacon. That's quite unique. Then the usage of bits in this malware for persistence. Haven't seen that before and haven't seen it since. So very surprising. And last but not least, I hope I was able to share some of the ways you can analyze COM, why it's powerful, why you'll encounter it most likely in many malware samples, and hopefully gave you some tips on how to do analysis of it more efficiently, because sometimes it can be quite frustrating if you have to deal with it. But overall, I thought this was a very cool malware sample, good case study to share some unique functionality, share some analysis techniques. And I would like to thank you again for joining me here. I'll leave you with some resources. I think those slides will be shared with you afterwards. I'll work with some of the organizers to arrange for that. Just some resources for the deobfuscation tools I used, more information about bits and COM, and also about that UAC bypass if you want to check it out. Thank you very much for having me. If you have any questions, please feel free to reach out via Twitter, via email, or I'll also be available here to answer some questions live, I hope. Thank you very much.
Hello, I'm Kevin Alejandro Rowdy, and it's an honor to be with you today here at CERT Norway, speaking to you on behalf of Norton LifeLock on the topic of creepware. Specifically, creepware is the set of apps that extend intimate partner violence into the digital world. It includes a broad variety of types of abusive apps. Many of them are focused on spying, others are focused on harassment and other issues. Before I dig deeper into the topic, I want to warn that this talk will touch on intimate partner violence, which is an important issue, but also one that can be difficult to listen to. So intimate partner violence is pervasive. It includes domestic violence, and victims are often repeatedly harassed by very determined adversaries. In Norway, 27% of women experience intimate partner violence in the course of their lifetime. The statistics are similar in the United States and in the rest of the world. In the US, 25% of women and 10% of men will experience IPV. This amounts to about 20 people per minute, which is a pretty shocking statistic. We really wanted to understand how technology is involved in all of this and how it enables abuse in the digital world. So we conducted a survey in 2020, February of this year, among US adults. And we found that nearly half of the participants admitted to stalking a current or former romantic partner. And 10% of those partners admitted to using a mobile phone app to monitor some aspect of the phone's private communication, such as SMS, messages, phone calls, emails, or photos. I mean, the list of sensors on a device is so thorough, there are all sorts of possibilities for spying there. There are signs that technology enables a broad variety of intimate partner violence beyond spying. These reports here are indications of the variety of different types of harassment, spying, hacking, physical device access, the creation of fake revenge porn, and other issues that are affecting survivors of intimate partner violence and making their lives more challenging. So we really wanted to understand the technology that's behind these attacks and what we could do about them. So we've conducted 2 studies in collaboration, the first one with Cornell University and New York University, and the second one in conjunction with the same team at Cornell, but also with the University of Michigan. And in the first study, we really wanted to understand what types of creepware are out there, what kinds of abusive apps are enabling interpersonal attacks. And so we developed a novel algorithm and methods to really measure the instances of these apps and to discover them and take action against them. In the second half of my talk, I'll touch on the role of customer support that customer support at a security company can play in supporting survivors of intimate partner violence. So first of all, what is creepware? So as I mentioned previously, it's software that enables abusive behavior. In particular, there are many mobile applications that help people to behave like creeps in the sense that it enables a broad variety of abusive behavior. To this end, we conducted a measurement study. Its goal is to discover and understand the types of creepware that are being used in practice. We'll proceed by first presenting background research and data sets that motivate and enable this work. Next, we'll describe the customized graph algorithm we created to measure and find prevalent creepware. Third, we'll talk about the taxonomy we created to characterize the creepware ecosystem. And we'll provide a few representative examples of what we found. And we'll continue by talking about what we're doing to take action against this creepware. So the central question we're trying to answer with our measurement study is the following. What kinds of apps are most likely to appear on devices infected by intimate partner spyware? We set about to design an algorithm that would answer this question exactly. Now, intimate partner spyware is a well-known issue. We built on a 2018 study that systematically identified the spyware used in intimate partner violence. They identified candidate spyware apps by searching for mobile apps that advertise under such terms as "catch my cheating girlfriend," and thus surfaced a large number of candidate apps, some of which they manually labeled. And then next, they engineered a feature set around the available app metadata, which they used to train a classifier. Now, this is a very prescriptive approach, right? They identified these candidate apps that they were looking for, all focused on spyware. All of their terms were focused on spying, and they were able to identify very reliably a large number of applications of this nature. Our goal was a little bit different. We wanted to capture the broader ecosystem of abusive apps. So we turned to complementary techniques that don't use descriptive features at all. Instead, we rely on the simple insight of guilt by association. This is an approach that we've used very effectively in the past for detecting malware and different types of threats. And we thought it could give us a lot of insight in this situation as well. You can think of this as the insight that birds of a feather flock together. And prior work has shown that installation relationships do indeed identify clusters of malicious software and clusters of benign software. And so in this case, you can imagine that the type of people who would install an intimate partner spyware application would be likely to install a broad variety of additional abusive applications. So by studying like software installation patterns, we can create useful groupings that can help us to identify this problem. And another benefit of this is we only need a small labeled set of known intimate partner spyware so that we can seed an exploration of the broader ecosystem of abusive apps. So we started identifying a set of apps that were focused on intimate partner spying and that were openly advertising for use in this arena. And so you can see here on the left, Hello Spy openly advocating intimate partner violence with its imagery and its marketing. On the right, you see MSpy and all of the features that it enables, which ranges from social media surveillance, call log monitoring, SMS tracking, location monitoring, photos, videos, browsing history. Many apps also can turn on the camera remotely, the microphone remotely, etc. You can also see apps like Girlfriend Spy very openly advertising for the use case that they feel is most appropriate for their app. Now, we know people are installing these applications, and so we want to leverage what we know about these bad apps to identify additional malicious applications that we don't know very much about. Each bubble here represents an application. Some of them we know are malicious, others we don't know much about. They could be benign or malicious. Basically, the intuition of our algorithm is to look at the devices that are installing these apps. So if we can see here a couple of devices that are infected with intimate partner spyware, and now we want to see, okay, what other apps are very likely to appear on those kinds of devices. So by looking at, for any app, at the devices on which it's installed, if we see an app that's disproportionately likely to appear on an app on which we see intimate partner spyware, we can be pretty confident that that is a very suspicious app that has abusive potential. Why do we think this works? So before we really dove into creating the algorithm, we took a look at devices on which we could see the presence of intimate partner spyware. And we could see several other applications on these devices that had clear signs of abusive potential. So here's an example of a real device on which the MSpy application has been installed alongside Girlfriend Cell Tracker, the hidden auto call recorder, location tracker, and an SMS forwarder. So together, all of these apps are clearly being used to spy on an individual. And so we saw a lot of devices of this nature that gave us confidence that this approach could work. So if we can see these apps being installed in the context of an app that we know is used in intimate partner spying situations. So to give you a better sense of how we went about developing this algorithm, we started on 2017 app installation data. We're looking at 27 million devices, nearly 11 million apps, and 4 billion installations of those apps on devices. You can think of this data set as being formatted in the following way. For every device, we have a list of the apps installed in this device. We're not including any sort of identifier for the device. All we're providing is just a list of apps that are installed together. We represent this in a bipartite graph between devices on the left, 27 million devices, and nearly 11 million apps on the right. We add an edge between a device and an app if the app is installed on the device. And as you can see, we have 4 billion app installations in 2017. We're also specially designating 18 intimate partner spying applications that have been identified in the previous research as apps that we know are openly advertising for this purpose and that we would expect to exist predominantly in situations where the goal is to perform intimate partner spying. We've also run this on more recent data. 2018, 2019 data has similar statistics. It's a year's worth of data kind of splitting between 2018, 2019. We've also run this on 2020 data. And I'll share later a little bit of trends of how the creepware ecosystem has been evolving since the beginning of our study in 2017. So to give you an overview then of how this works as we take the data, we pump it through our pipeline. We start with this anonymized data and we represent it as a graph. We remove anything that looks like it might not be a typical device. Like if there's a device that looks like it's used for testing, we'll remove it from the data set, etc. Then we represent everything in this form of bipartite graph. We're labeling 18 apps that are known to be used for intimate partner spying as ground truth in this graph. And then that forms the input to our creep rank algorithm, which is our graph algorithm. It's a distributed Spark Scala job that runs for 4 minutes, and then it converges after about 10 rounds. So effectively what we're doing is from these apps that we know are malicious, we're updating our scores progressively until we reach kind of a convergence of scores. So we can see for every app, how likely is it to appear directly on an app where we know there's intimate partner spyware, or indirectly, is it closely associating with other apps that directly appear on devices where there's intimate partner spyware. The output of our algorithm is a ranked list of the apps that are most likely to appear on infected devices. So taking this input data to the output data, we created a taxonomy over the top 1,000 apps that came out of this algorithm. We took 4 researchers who iteratively developed this taxonomy over the top 1,000 apps. And we identified categories and subcategories of the software that we found on these mobile devices. So what did we find? Our seed input set of 18 apps were all intimate partner surveillance apps. They were very thorough in the way that they would spy on a device's sensors. Now, we found many other types of spying applications as well. So the most prevalent category was social media, followed by location sharing apps, and then by very thorough surveillance applications that monitored multiple sensors. We also found a broad variety of additional apps that were focused on a very specific use case, either spying on call recordings or call logs, being able to remotely turn on the camera or remotely turn on the microphone, monitor the screen, monitor text messages, monitor social media in a covert way, etc. So we expected to find these results, right? But given the way that our algorithm works, it's very open-ended. It can detect anything that's very likely to appear alongside thorough surveillance applications. And we found a broad variety of creepware applications that fulfill many additional abusive purposes. So we found many, for example, caller ID applications that monitor location, apps that control the way the phone is used. We even found apps that defend against these attacks. Evasion, we found evasion apps, harassment apps, information extraction apps, and spoofing apps. So I'll go through each of these categories now one by one and give you a little bit of a better sense. We started by talking about surveillance apps. As I mentioned, these apps are particularly designed to spy on a phone in a variety of different ways. I'm not going to dig too deeply in this, but it is interesting to see how many of the applications are focused on a very specific spying purpose and on doing that very well. Now, the spotlight's been shined on these apps for quite a while, so one would hope that we'd be able to be making progress against them. And in some ways we have. There are fewer applications that are openly advertising under terms like Catch My Cheating Girlfriend, because Google and other app store owners have been blocking these applications and trying to prevent advertising under those terms. However, much of what you see is just more subtleness in the way these apps are being advertised. So here's an example of an application. Its identifier on the Google Play Store is com.omrup.cell.tracker. It used to openly advertise under the term girlfriend cell tracker. And now, as they saw that Google was evolving its developer policies and its app store rules, they quickly pivoted and renamed their app Family Locator Safe Zone to give it a more innocuous sounding name and use case. And they managed to switch their description of the app quickly enough that Google has actually not removed this app from the Play Store, even though it still has the same functionality. It's just marketing itself in a different way. Now, most of the other forms of creepware are severely understudied, and there had been very little understanding of how these apps could perpetrate abuse. A broad category of apps that we found were spoofing apps. Most of these are purely malicious. Burner phone apps are basically an application that will give your cell phone an additional phone number for you to send calls or text messages from. Now, there are plenty of reasons for which you would want to do this. It's effectively like having a virtual SIM card in your phone to allow you to have an extra number. But in an abusive setting, you can see how this would be used. One of the first things that a victim would do to an abuser who's harassing them would be to block their phone number. Now, a burner phone enables a harasser to basically evade blocking by having another number that they can switch on a regular basis and still continue to perpetrate abuse. There's another broad variety of applications that are all about impersonation and falsifying alibis. So these will basically enable a person to send an SMS message or a social media message from a fake account and enable them to impersonate the identity of someone else. So we'll see an advertisement momentarily for these types of app. The voice spoofing apps are interesting. They'll enable a man to sound like a woman or a woman to sound like a man, or sometimes they'll just create a very scary sounding voice, etc. So that's just adds another layer onto the spoofing apps that are out there. There are a variety of other apps, like for example, image spoofing apps will often enable pasting a person's face onto another person's body. This has been shown to be used in creating fake revenge porn. We're able to identify some of the apps that are most likely to be used by abusers for this particular purpose, because they're showing up on devices where there is a lot of abusive apps already installed. So let me show you kind of a typical example of one of these spoofing apps and how it could be used.
Hey, hello. Ugh. Don't like your buddy's girlfriend? Well, break them up.
You can see from this video, they're very openly marketing it as a tool for basically disrupting a person's relationships, right? And one of the first things that is kind of in an abuser's playbook is to isolate a victim from their support network. And it's pretty clear how this application could be used and how dangerous it would be in the hands of an attacker. They can either impersonate their victim's loved ones, or they can impersonate the actual victim themselves and send hurtful messages to that person's support network as if they were coming from that person. There are a broad variety of additional applications that are tutorials. These are apps that teach abusers about the kinds of apps that are out there that they could use. The advice spans a variety of different things, including how to hack a device, how to surveil on a device, how to use harassing applications, how to root a device so that you can install a more invasive surveillance application. It talks about a lot about hidden Android system settings that can enable like behavioral logging for different apps and things like that. Spyboy covers almost all of the creepware categories that we've identified in our study. And whereas there are other apps that are more focused on how to spy on someone's device, and all the apps are basically spyware apps. There are a variety of different types of harassment apps out there. One of the first ones that kind of jumped out at us that we were not expecting are fake surveillance apps. And so they self-describe as harmless pranks, but you can see here from a comment on one of these applications that basically gives a fake location for somebody, and they can really cause a lot of trauma. Basically, the way that most of these apps would work is that the abuser brings up an app that gives the illusion that they have some sort of hacking superpower, that they can hack the person's Facebook account in real time, or their WhatsApp account in real time, or the actual device. And the application would be installed on the abuser's app, and they would show it to the victim and say, look, I'm hacking your phone right now. And it would show like a variety of screens where it's basically in process of hacking, and then it'll start scrolling and showing a bunch of messages or files, folders, etc., that are purportedly from the victim's device. Now, if the victim could see those in detail, it wouldn't stand up to scrutiny. But maybe an even more common type of abusive application is what we call SMS bombers. So you can see here in this video, this is me with an attack phone and a victim phone. And basically what this application enables is it enables the abuser to basically send text messages from this device to the victim device, and to do it repeatedly. They specify the frequency, the number of times that the message is sent per second or per minute, and they send the total number of messages that they want to be sent. And they can basically just spam the victim's phone with either phone calls or text messages on a very repetitive basis. There are a lot of information extraction apps as well. These are similar to surveillance applications, but they're more like one-time content dumpers. So if the abuser got access to the phone, to the survivor's phone, it would basically install one of these information extraction apps that would pull in a bunch of content, extract content, and upload it to a different device. They'll often be focused on trying to recover deleted images or deleted files, pull all the contacts, etc. There are also many hacking apps in this category. They're not apps that perform continual surveillance. They're more like apps that will pull in a lot of information all at once. We also saw a lot of people search applications. They basically purchase data from a broad variety of public sources, and they use it to provide information about a person's address history and phone numbers, etc. All right, so most of the creativity we saw on display among the creepware apps was generally very depressing for obvious reasons, but it was somewhat comforting to see some very creative and quite cool defensive apps as well. So in addition to basically just anti-spyware and antivirus type of applications, we found a lot of applications that provide access control on a device in creative ways. Here's an example of an app called Oops App Lock. And the idea is that imagine there's an intimate partner violence survivor who's living still with an abuser. They could install Oops App Lock on their device. And what it does is it gives the illusion that the phone is frozen and non-functional. So it might be frozen on like a browser page or on just like a generic app page or something like that. And none of the buttons on the phone will be responsive, and it'll look like the phone just doesn't work or it's frozen. But if a secret volume pattern of key presses is set as input, then the phone will unlock. Other examples of access control applications are apps that will make it impossible to answer a phone call without inputting a password first. There are other varieties as well, and you can see our paper for more examples. A sort of semi-defensive category that we found was quite interesting. These are evasion applications. So a survivor of intimate partner violence might not be able to completely remove malicious applications from the phone, but they can hide content that they don't want to be seen on the device. And so there are quite a few apps that hide secret content but behind like camouflage facades. So here's an application that just looks like a regular calculator application, but if you type in a specific equation, it will unlock a cache of secret hidden photos. Here's another one. Some of these masquerade as currency exchange applications, etc. And then once they're opened up, you can see inside that there's like all of these hidden applications. It has other functionality as well, like it can freeze and unfreeze applications, etc. Finally, this is kind of back to the controlling side of things. There are a couple of apps that are quite alarming in the sense that they basically hack and issue a denial of service attack against the device to knock it off of the Wi-Fi network. So Wi-Fi kill and netcut are the most prominent examples of this. But there are other applications that can be used to exert control in the sense that they will hide the presence of any arbitrary applications on the device. So assuming that the abusers installed multiple abusive applications, they can open up this app and just select the applications that they want to hide from the launcher on the device. That's a very alarming functionality, frankly, but fortunately, as of Android 10, the newer versions of the operating system, it's not possible to hide applications from the launcher anymore. So so there is some good news for people with newer phones. So as I mentioned, many of these results I've been talking about came from analysis of 2017 data. We looked at this more recent time frame from May 2018 to 2019 and found very similar results. All of the same categories still existed during this more recent time frame, but there were some new trends. Some things had kind of fallen out of favor a little bit. There were fewer burner phone applications, possibly because there's more access to dual SIM card phones, etc. On the other hand, there were a lot more hacking tools that we were seeing. There was a lot of additional social media surveillance, a little bit less on the fake spying app side, but the same ecosystem exists. There's just a little bit of evolution over time. And as I mentioned, the way that the apps are marketing tends to be less explicit in terms of enabling intimate partner violence. So they tend to be more of a dog whistle in terms of how they're like trying to attract the customers that would would be interested in spying on an intimate partner without like explicitly marketing their application that way. And very often what you see are disclaimers saying, please don't use this app for intimate partner spying. Or if you put this app on an adult's device, you need to tell them that you did so. It's very clear from that kind of warning that the app itself is as hidden and as evasive as possible, but they try to put their legal responsibility on the app users. We've made some progress towards combating creepware. Since July 9, 2019, we released a new feature in the Norton Mobile Security application. It's been warning our customers about any surveillance-related applications. So here you can see an example warning. In addition, we reported more than 1,000 apps to Google. They determined that more than 800 of them violated their developer program policies, and they removed them from the App Store. So in particular, here are some examples of the rules that many of these apps violated. They're either spying or they're misleading. We also found apps that generate fake ID cards, found apps that try and recover credit card numbers from people's devices. We found a lot of hacking apps, and then also many of the apps try and excuse themselves. So they're saying that they're designed for pranking and humorous jokes, essentially. But the App Store's policy very specifically states that that is not a sufficient reason. And Google is continually trying to do their best on this problem, but the number of apps that are proliferating is high. And in our conversations with them, if an app has a very strong claim at a benign use case, it's been difficult for them to find legal justification to take those apps down in some cases. So the problem still is out there and exists. And in addition, a lot of third-party app stores are indexing a lot of these old applications that have been banned from Google Play, but that are still accessible to people. All right, so that's a whirlwind tour of the types of malicious creepware and surveillance applications that are hurting survivors of intimate partner violence. So one of the next things that we wanted to be able to look into is the issue of customer support and providing better customer support for victims of intimate partner violence. You could imagine serving as a customer support person is probably a stressful job to begin with. But if you receive a call like this with limited training, it could be overwhelming. Here you have a case of a customer complaining about stalking by an ex-boyfriend. The mobile app isn't finding it. The evidence of this, they want to find the name of the program so they can prosecute, and they're very concerned, clearly. Now, in many cases, our customer support folks don't actually find a malicious app on the device. And in many cases, customers are not aware of how the spying could be perpetrated. There are many additional ways that go beyond stalkerware. And so we really need to have an informed and a customer support organization that can deal with these kinds of issues and be prepared so that they don't panic in the moment, right? Here's another example that illustrates even like a more extreme case where the customer is in an emotionally very distressed state. And dealing with this type of a call as a customer support person with limited training is a very kind of dangerous and stressful situation, and one in which they won't be able to help as well as they would like to because they don't really understand what they need to do. So we want to be able to improve on the status of customer support. You see here, traditional customer support assistance emphasis has mainly been on the removal of any known malicious applications. Many issues are left out of scope, and customers really need to be able to take better care of their account passwords in most instances. Many times the spying is happening through knowledge of account credentials, etc. And so we need to be able to help customers by educating them on these things and providing detailed guides for how to better secure their account credentials. Right now, we have step-by-step guides for removing stalkerware, but that's not the full scope of the issue. There are also many misconceptions by the customer support staff and by customers that need to be addressed. For instance, customer support staff aren't always aware that SMS forwarding is possible. In other cases, they might think that their app, their security app is almost infallible. And so it's important to give customers a realistic understanding of what the app can do and what it can't do, and help them to address the other issues and point them at resources. some of the basic questions we wanted to understand are, what should the role of a customer support specialist be? They're often on the very front lines with survivors of intimate partner violence. And if these people were instead going to a domestic violence advocate or a center, they would get help with safety planning. They would get help with many other things. So what is the split between the responsibilities and ideally of a customer support specialist and some of the other advocates that are available to survivors of intimate partner violence? These are some of the questions we wanted to ask. We wanted to also understand under which circumstances there should be referrals to these advocates. In some cases, contacting the police seems appropriate. What are those situations? We also want to create better resources for customers and for the community at large. So we're working with the Coalition Against Stalkerware to develop better trainings and to really resolve some of these issues on behalf of all security companies. To have a better understanding of these issues, we turned to graduate students at the University of Michigan and at Cornell Tech, and also faculty who met with intimate partner violence advocates in New York City and in Michigan. And they asked them questions about the status quo of surveillance detection technologies in security apps. First, they wanted to know if the warnings being issued by these apps were understandable and appropriate, and if the notifications were likely to go to the right person, what safety issues there might be, etc. And in addition, we asked them many questions about customer support. We provided them with realistic scenarios derived from actual customer support sessions in which there were a broad variety of representative issues that come up when someone in an intimate partner violence setting reaches out for technical support. We wanted to get answers to many of these following questions and issues. Who should be conducting safety planning? To what extent should customer support individual focus on safety planning? How much forensic investigation should be done? Should they be focusing on compromised accounts, or is that out of scope? Should they be trying to fix settings on the device? Should they be educating, and how they should be educating the customer supports about keeping their accounts safe? And at which points should they refer to local advocates and other resources when the person is either in physical danger or in distress and needing additional support? On the basis of this feedback, Allison and Anam Tahir from Cornell Tech developed a training for technical support staff. And they identified the main issues and tried to identify what should be in scope and out of scope. They identified many helpful suggestions, such as and steps that a customer support person should engage in a call. First of all, they need to know when tech abuse is happening. They need guidance on how to interact with the customers experiencing intimate partner violence. In terms of giving advice, we have the advocate's advice of what should be included and not included. We also got a lot of helpful guidance in terms of how to deal with issue escalations and referrals. And the people who are providing the support need to take care of themselves and to deal with secondary trauma that might arise from fielding these calls. So in addition to providing a detailed training that we're sharing with members of the Coalition Against Stalkerware, we also developed a cheat sheet for customer support staff that includes the main elements of a call in this space and what things they should consider saying, what things they should avoid saying, and why. We hope this will be very helpful to customer support staff as they field these calls and figure out how best to serve the customers. We're engaging in additional open research questions, and there are many open problems that we haven't really gotten the best possible grasp of yet. In particular, notifying customers of stalkerware on their device is a challenging issue. You want to make sure that the notification goes to the survivor of the violence and not to the perpetrator. And so this is challenging in particular because it's the abuser who generally installs the app on the device. And so you need to be very certain that you're not just providing a one-time immediate warning. You need to be able to provide the warning to the survivor when the survivor is using the phone. As I described, we've created a lot of customer support training materials, and we're working to disseminate those. There are some other issues that are daunting and difficult to get a grasp on. So in particular, a lot of these apps exist primarily on the attacker side. So for example, the harassment apps and a lot of the spoofing apps are on the attacker's phone. So it's difficult to notify the victim in these situations. We can hope to communicate with the attacker and maybe persuade them not to carry out the attack, but we're not going to be able to notify the victim in most cases. And finally, government policies throughout the world do not hold app developers to account for creating surveillance applications. And most of these developers are going unpunished, and you see a proliferation of new Creepware apps all the time. And so we would love to be able to see positive steps taken in the legal world and in cooperation with law enforcement to be able to hold these app developers to account for their actions. All right, so that's a high-level summary of some of the work that we're doing. It's been a pleasure presenting this work to you. I look forward to the question and answer session that we'll have later. And for any more details, please refer to our papers. One of them is available, and the other we hope will be available very soon. Thank you.
So hopefully you enjoyed the Malware Forum. We have really nice talks from Moritz, from Kevin, talking about different aspects of malware. And indeed, malware become quite a challenging topic in cybersecurity, because before we had computers, now we have multiple devices, different communication, new attack vectors that we haven't seen before. So it's a multiple things that make this topic very attractive for the researcher, for the organization that work with security. As I mentioned before, we have multiple directions that we are exploring together with postdocs, PhDs, master students, and bachelor students. I'm going to give a short overview of our activities, what kind of things we are doing and what kind of things we are working on. So first of all, it's a static malware analysis. So static is something that we take the malware and then we try to extract some features, attribute that we don't really need to execute. But the problem that we have so many different features like byte sequence, opcode analysis, we have portable executable header, and so on. So putting them together and then throwing at AI won't really work. So you need to understand which malware you need to analyze, what kind of machine learning methods you need to use, what kind of features you need to use, and how to present findings. This is one of the direction, and then it's basically a lot of about numerical features. So numerical features are something that we can extract, like number of bytes in the file, number of bytes in the specific section. I don't know, number of API calls, and so on. So something that we can extract can be a limited amount of things. But the problem that if we have like huge amount of features, we probably need quite heavy computer and quite heavy computational load to process this model. So one of the things also for us to find a few features that really work. You can see from this picture that we also try to understand how well the machine learning works on the multi-class classification, like detecting types, families. Well, apparently it's not that easy when it comes to several hundreds of families. So apparently we need to find more efficient way. However, one of the challenges is that static analysis can be challenged by things like obfuscation and encryption. So to make it easier, we need to find something additional, like about internal functionality. So for this, we are using dynamic malware analysis. So not just having the, let's say, the sandbox execution of the malware, but also having some kind of machine learning that can be used to train from this extracted data and then make a successful detection model. So this is one of the direction that we are trying to explore. Many people use deep learning as a one-size-fits-all solution. In our case, we try to do it, increasing the number of layers, increasing the size of abstraction. But the problem that we can't really get a normal, let's say, detection rate through these. So it means that we need to explore something additional, like how to make these features better. One of the also another works is the behavioral malware analysis, so something that we try to see what kind of actions malware perform on different level of granularity to detect the sequence of potentially malicious software. So Sergey is working on one of the topics related to entry point detection, like how to detect malware before it becomes malicious. It's very interesting talk, very interesting topic, because you can see that we have the auth-generated activities like the process creation, process launch, and then we have also the entry point for the malware, meaning that we need to find a way how we can do the analysis of read-write operations to detect and to predict that this is most likely a malicious file and malicious activity. Right, thank you very much for your attention. I hope you really had a good time, enjoyed the talks. It was very fruitful discussions. Here today, lots of questions. If you have any comments and if you have any suggestions, please shoot us email, and I hope to see you all in 2021. Thank you for your attention.